Hi, ladies and gentlemen. I'm Jun. Today, I'm going to introduce our work, non-exhaustive learning using Gaussian mixture generative adversarial networks. At first, I will introduce the background. Non-exhaustive learning is an emerging machine learning paradigm. It embraces the challenging that training data doesn't have instance of all class that may be expected in the test data. Why it is important? Because conventional supervised learning method will 100% misclassify such instances. Also, the data distribution changes over time, which may cause new classes emerge naturally. In table 1, it presents the related task of non-exhaustive learning. The first column is the abbreviation of the task. The second and third column present what information each task may need. The last column present the goal of the task. For example, for both train and test data have a known class and self information in the conventional tasks. On the contrary, non-exhaustive learning incrementally learn the test instance with unknown labels and self information. What is the main challenging of non-exhaustive learning? The first, the recognition of emerging classes needs to be performed online. Second, the number of instances for emerging classes may be very small. The number of new emerging classes in test data is unknown. To embrace this challenge, we propose a new non-exhaustive learning model called non-exhaustive Gaussian mixture generative adversarial networks. Our model takes multi-model prior as input to better fit the real data distribution. Also, generative approach using GAN helps overcoming the challenging of small number of instances for the emerging classes. Our model uses Bayesian approach to detect the number of new emerging classes in test data. We want to introduce the background of GAN. GAN has two main components, generator and discriminator. Generator attempts to generate a fake instance through the discriminator. Discriminator tries to distinguish these two type of instances. They are playing a zero-sum game. By GAN also has these two components. Also, it has the encoder. It used the encoder to encode the data into the latent space, which ensure the reconstructed instance more close to the real one. Next, we will introduce the model architecture. In the right-hand side, it shows the workflow of our model. At first, our model takes the instance from the training set. We assume that we already know the number of classes in the training set. After that, our model computes multi-model prior distribution by Gaussian mixture model, and then reconstructs the instance via bidirectional GAN in offline phase. For online detection, our model compute the loss between the reconstructed instance and the test instance. We propose an unknown class scored function to filter out this instance most likely belonging to the new emerging classes. Then we propose the infinite means algorithm to estimate the number of the new emerging classes. At the end, our model recaptures this instance for subsequent recognition. Next, we will introduce the I-means algorithm. This is the one of most important component in our model. The figure in the right-hand side presents the how I-means algorithm works. At first, we find out the minimum loss to each existing cluster and select the closest cluster CK to the new instance. In other words, this instance potentially belongs to CK. Then we employ Bayesian approach to make a binary decision whether this test instance belongs to CK or an emerging cluster. This decision follows Bernoulli distribution with parameter theta k. In the warm-up stage, we apply the free sigma rule to compute the beta priors by updating the shape parameter alpha and beta. After the warm-up stage, we employ the map estimation to obtain theta map at which the posterior reach its maximum value. After estimating the theta map, we make a cluster membership decision based on this parameter. After each decision, corresponding parameters will be updated. In the experiments, at first we will introduce the data set. We use 3 network intrusion data set and 1 synthetic data. We list the unknown classes in the last column of the table. Here we use two evaluation metrics. The first, we use the F1 score to evaluate the performance of unknown class extraction. Also, we propose a new metric called symmetrical R-square to evaluate the prediction of the number of the unknown classes. If the SR square close to 1, it means that our model defeats the competing method. If SR square equal to or close to the -1, it means that the competing method is better. Otherwise, if the SR square is equal to 0, it means both methods have similar performance. The motivation to propose this metric is that conventional R square would be less distinctive if two methods get much worse prediction. Also, baseline sometimes achieve better performance, but R square cannot reflect this scenario as its range is from -infinity to +1. So we propose this SR square to evaluate the prediction. In this slide, we are going to examine capability of unknown class extraction. In table 4, F1 score from our proposed model by using different prior. It shows that our model using the multi-model prior gets better performance. In table 3, we compare our model with other 3 competing methods. The result indicate that our model suppresses the competing method in most data sets. And in this experiment, we use SR square to evaluate the prediction. We compare our model with X-means and NE-GM-GAN because both competing methods can detect the number of new emerging classes. The result indicate that our model outperforms the competing methods. In the synthetic data, our model achieved comparable performance as the X-means. However, NE-GM-GAN has worse prediction, so the SR square is equal to 1. In this slide, we also visualize the prediction. Our model achieved robust prediction across 4 data sets. In conclusion, we propose a new online non-exhaustive model, non-exhaustive Gaussian mixture generative adversarial network that synthesizes Bayesian method and deep learning technique for incremental learning the new emerging classes. Our model consists of 3 main components. First, Gaussian mixture clustering generates multi-model prior and recaptures both KC and UCs for parameter updating. But second, bidirectional adversarial learning reconstructs the loss for extracting independent unknown class from the known classes in an online test batch. Third, a no algorithm I-means estimates the number of new emerging classes for incremental learning the unknown classes on large sparse data set. That's all. Thank you.